Hello, I wanted to talk a little bit about the differences between different types of charts that we've been covering. So the pacemaker potential, the cardiac potential, and the ECG, and then kind of what's going on at different times. So I'm going to try to make this so that we can talk about all of them at the same time and show different pictures about where different things are, and kind of spread things out. Um, so let's start out by talking about the pacemaker potential. Now, the pacemaker potential is going to have a couple of different aspects to it. The first off is these slow sodium channels that are going to be present on the actual pacemaker potential itself. They cause this initial depolarization, which is also called step one. Once that hits threshold, it opens fast calcium channels, which will depolarize the cell, and then slow potassium channels will open, repolarizing the cell, which will then open the slow sodium channels, which will depolarize to go up to threshold, and then we just keep on doing the same thing. You can alter these slow sodium channels to make it so that it's either faster by opening things that will make it more positive, so sodium channels or generally calcium channels that will depolarize that faster, making it so that the slope of this will increase. Alternatively, you can slow it down. So the ones that speed it up, make it more positive on the inside, making it faster to get to threshold, are called positive chronotropic agents. They're altering the pacemaker potential. Alternatively, you can have negative chronotropic agents that are going to make this slower to get up to threshold. That would be things that would make it slower or more negative on the inside. Negative chronotropic agents make it slower. So you have things like opening up a potassium channel to let potassium out, or opening up a chloride channel to let chloride go in. So either way, negative makes it go slower. This whole portion above the threshold is going to be the same no matter what. It's just the speed at which it gets up to threshold. And remember that this is also happening only in the SA node of the heart. When that does happen, so that's going to happen in the SA node will go to the AV or to the atria, depolarize the atria. When they are depolarizing the atria, what it does is opens fast voltage gated channels in the cardiac muscle. So you could call this the cardiac potential. That will depolarize the cardiac cells. Then, at that same time, voltage-gated potassium and voltage-gated calcium channels are going to open. So this makes it so that there's a prolonged plateau that will make it so that everything will squeeze and stay and then relax. So this prolonged depolarization makes sure that everything gets squeezed out of it before relaxation. You can see this initial atrial depolarization through the P wave. The QRS complex is going to be the repolarization of the atria, the depolarization of the ventricles. This depolarization of the ventricles is going to cause contraction of the ventricles, and then a relaxation or repolarization of the ventricles will happen during the T wave. So P wave, depolarization of the atria, PQ, contraction of the atria. QRS is the repolarization of the atria, the depolarization of the ventricles. ST is contraction of the ventricles. T is the repolarization of the ventricles. Hopefully that all makes sense, and hopefully you can see how these all fit together.